All right, everybody, welcome to the seminar today. It really is my great pleasure to introduce our speaker, Dr. Masoud Negahban-Azar. And so he's currently an assistant professor of water research and environmental engineering, and currently leads the Water Security and Sustainability Lab in Environmental Science and Technology. And I think it's fair to say that collectively his group focuses on things such as water resource management, use and sustainability and processes, but then alternative sources of water, also investigating these things at the watershed scale, and also looking at different decision support tools for stakeholders and farmers. He received his PhD from Colorado State University in civil and environmental engineering, I believe, and before joining the University of Maryland, he was a postdoctoral fellow at Harvard. And you know, when I said that it's my great pleasure to introduce him today, it really is. It doesn't seem like too long ago that I introduced you for one of these talks for our seminar series, and since then, his PhD student Farshid gave a really great talk on using agent-based modeling and its simulations for looking at some of these processes at the watershed scale. And so I'll let you take it away, Masoud.
Okay. Hello, everyone. Thank you for coming to today's seminar. So today I'm actually going to give an overview of what we are doing in our lab, water security and sustainability, provide a couple of examples, and so that's it. Let's move on. So I'm going to talk about what we are doing in our lab, and then I'm going to talk about decision support systems that we are developing, because that is actually the outcome of the main outcome of what we are doing in our lab, to develop different decision support systems or decision support tools to help policymakers or decision makers in water resources management and water reuse. I'm going to talk about different aspects of decision support systems, different types of decision support systems, their use in water resources management, and then most of today's presentation will be on providing a couple of examples about what we are doing in terms of developing decision support systems. In our lab, we are actually focusing on three main research areas. We are working on watershed hydrologic modelings. We are trying to improve the available hydrological models, and we're also exploring water reuse and alternative water sources. So how we can implement alternative water sources such as treated wastewater or stormwater at a watershed scale, how we can use them in the scheme of integrated water resources management. And then using both of those, we are developing different decision support tools for better managing our water resources and also implementing water reuse or alternative water sources. So what is DSS, or Decision Support System? It's an interactive tool that decision makers can use in order to analyze data, documents, knowledge, models, in order to solve a problem or to make a decision. So that's in simple terms, what is a decision support system? There is different data flow in a decision support system. It could be user interactions, different types of data, real-time, automated, extended data source, and all of them, when we use them, we're going to get different outputs like alerts or reports in order to improve our decision process or to solve a specific problem. There are different types of decision support systems. It could be model-driven, data-driven, communication-driven, document-driven, and knowledge-driven. Model-driven, if they are based on different models in water resources management, for example, if they're based on different hydrologic models or optimization models, if they're based on different types of data, or based on different types of communication technologies. It could be based on documents like policies, regulations, those kinds of documents. And also they could be based on the knowledge, like expert knowledge, based on knowledge of different experts in the field. We can develop a decision support tool. In water resources management, they are extensively being used, and can provide you some examples. Let's say if it's a watershed, there could be many different ways of using decision support systems in order to improve water resources management. For example, if you wanted to look at the impacts of climate change, what would be the impact of climate change in a watershed? Or if we change a land use, if we change a type of crop, what would be the impact on, for example, the nutrients in the stream or the sediments? Or if you deforest, or if you have a development in a watershed, what would be the impact on the water quality? Or if you have in urban areas different developments or growth, what would be the impact on water quality and quantity in terms of irrigation? If we implement different types of irrigation projects, for example, water reuse or different types of water irrigation projects, what would be the impact? So these are some of the examples that DSS can help us to make our better decisions in water resources management. Now, I'm going to provide 3 or 4 examples from the projects that we have done in our lab in terms of developing different decision support systems. The first 2 or 3 projects will be mainly over the use of reclaimed water for, like this. The use of reclaimed water for irrigation. And it will be around 2 main questions. The first one is to develop a decision framework to identify suitable areas for implementation of reclaimed water for irrigation. So basically to identify the hotspots that are most suitable for reclaimed water use for irrigation. The other question that we have explored is to develop decision frameworks to test watershed scale models to assess the water budget and also the different water reuse scenarios and the impact on, for example, the crop productivity and the challenges that we have faced under this and how we overcome those challenges. This map is showing the global water stress. You see that in many parts of the world, we're facing a global freshwater stress. And if you, for example, look at US, this is, if based on climate projections, it has been projected that if we just keep the business as usual, we are going to have in many parts of the US water stress in year 2040. And we know that, okay. Looking at the water consumption in different sectors, agriculture uses most of the water. So most of the fresh water is being used in the agriculture sector. And once we have water stress, agriculture will be the mostly impacted by the stress in water resource stress that we are facing. And obviously food grows when water flows. If you don't have water, you don't have food. With this little background, now let's get to some of the projects that we have done. I'm going to provide a conceptual framework that we have developed in our group in order to develop those decision support systems. So first, we did a data collection, as you can see on the left, collecting data from different resources and then classifying those data to then use a GIS MCDA or a spatial multi-criteria decision analysis. So with the use of different techniques like analytical hierarchy process or different MCDA techniques, we developed different spatial multi-criteria decision analysis, then to use those decision analysis frameworks to develop decision support systems with the help and integration of those decision frameworks to hydrologic models, and then to provide decision support tools for better management of water resources using SWOT model. For our study area, we selected two states, California and Maryland, with 2 totally different climatic and geographic conditions. And I'm going to provide one example from each of those states. First, let's talk about the GIS MCDA framework that we developed. In our framework, we looked into different decision criteria and then use an analytical hierarchy process in order to spatially analyze our study area based on those different decision criteria, then combining those spatial MCDA or multi-criteria decision analysis in order to identify that hotspots that are most suitable for agricultural water reuse. The first case study I'm going to talk about is the case study of California. I'm sure you have heard about the drought in California for the past few years. California has been facing droughts in many years in the past 15 to 20 years. And agricultural sector in California is impacted because of those prolonged droughts in the state. And these are some of the maps from the drought monitoring website. And there are some consequences of that drought. So water supply issues, mandatory conservations, less wastewater flow, lower quality, and water rate hikes. And this map is showing the agricultural activity in California. As you can see, most of the agricultural activity is happening in the Central Valley, with some activity in the Imperial Valley in the south and some other areas, but mostly in the Central Valley, California. We wanted to explore and develop a framework in order to identify the hotspots that are most suitable for agricultural water use for the state of California. We developed 5 decision criteria. First one was reclaimed wastewater sources in terms of the amount, the quality of the water, and the location of the wastewater treatment plants. We looked at land cover, or basically the type of crops that are growing in different regions of the state of California, and the location of the farms. The water policies, this goes back mainly to groundwater condition, because there are in California, there are some areas that are suffering from groundwater decline. So we looked at the groundwater classification and prioritization in the state of California. We looked at the irrigation status, how much water is being used in different locations, in different farms in California, and how much water is being extracted. And also we looked at the climate condition. So not everywhere in California has the same vulnerability to climate change or drought. So depending on the location, we looked at different impacts of climate change on the agricultural sector in different locations in California. This is the decision framework that we developed. So reclaimed water sources, the processes that they use, the amount of treated wastewater, the treatment technology, and the distance from the farm to the wastewater treatment plant, the land cover. So we divided that into the 6 groups of 3 of them non-food crops and 3 of them food crops, because depending on the type of crop and based on the regulations for water reuse in agriculture, we cannot irrigate all types of crops. So you have to look into different types of crops and also follow the regulations. We divided those based on the regulation in California. We looked at the climate change, used the Palmer Drought Index to prioritize different locations in California in terms of vulnerability to drought. We looked at groundwater basin prioritization map, and also the irrigation status, if they're using groundwater or surface water, and how much water they're using or extracting, and how much water is needed in agricultural sector in different areas. Then we reclassified the area using AHP technique and overlay those areas. So it's in a spatial process. We overlay those areas then to identify the hotspots that are most suitable. But this is a summary. I'm not going to go over this. I actually presented a detailed seminar about this specific project last year. So I'm just going to show you the results. So this is the land cover MCDA, overlaying it with climate impact or drought index, then also with water consumption, groundwater basin prioritization, and the location and treatment processes of wastewater treatment plants. Once we overlay all of those, this is what we get as our decision support system. So in any specific location, so this is an example of those boxes that you see where there are wastewater treatment plants, then there are some crops or some recommendation in terms of which or in which areas wastewater reuse is more suitable. And for this case, we looked at grapes and almonds because of many different reasons, but just to let you know some of them, they are permanent crops, they are high value crops. As a result, they are more vulnerable to drought compared to, for example, annual crops like strawberry or tomato. And farmers, if they don't irrigate, they're gonna face a huge economic loss. So we selected those almond and grapes, and these are what you get. So for example, if this is a wastewater treatment plant in Central Valley, it's in Fresno County. These are the farms, almond farms, these are the grape farms that this wastewater treatment plant can provide reclaimed water for use in this radius. So this is an example of developing a decision support system for the case study of California. Now let's talk about Maryland, another case study. In Maryland, although we are getting a lot of rain, but we are also during some years facing droughts, not similar to California, like prolonged droughts, but periodic droughts or seasonal droughts. And another thing that we are facing in Maryland is the shift in the amount of precipitation and temperature. These are the two graphs. The top one is looking at the precipitation during the spring season from March to May. The bottom one is actually during the growing season. As you can see, in the past 120 years, we see a decline in the total amount of precipitation that we get during the growing season, but versus spring season, we are seeing an increase in the amount of precipitation that we get. And not just that, but we are also facing variability in the amount of rain that we are getting in Maryland. This is a very interesting example. If you remember in 2018, there's an interesting story in July. The first 2 weeks of July, right in the middle of the growing season, we didn't receive any rain. So rainfall was 0. It was driest on record. And then in the second 2 weeks of July, we received close to 17 inches of rain. It was second highest on record. So that's an interesting example of the rainfall variability that we are facing. So although we are receiving, if you look at the total amount of rain that we are getting in Maryland, it's a huge amount. But if you look at those variabilities and the shift in the amount and timing of the rainfall, that's the reason that farmers are using irrigation more and more compared to like 30, 40 years ago in Maryland. If you drive by to the, to the Eastern Shore, you see that farmers are implementing more irrigation compared to like 10, 20 years ago because of those variations in the rainfall. This is another driver behind looking at water or alternative water sources. If you look at these are the 2 monitoring wells in coastal plain Maryland, you see the decline in the past 30, 40 years, the huge decline in some areas close to 70 feet in the groundwater level. And just to emphasize, the only source of fresh water in the Eastern Shore is fresh groundwater. So both urban areas and agriculture are pumping from the groundwater in order to provide urban water or irrigation water. So there's also a competition between urban and agriculture in Eastern Shore, Maryland. Talking about those drivers, now let's talk about the decision support systems that we had developed. Same process, but different decision criteria. So we looked at water policies, but we don't have a groundwater basin prioritization map in Maryland. We developed based on the number of wells and the amount of water that is being pumped. So this is something that we developed for this project. Compared to California, we were able to obtain it from the California Water Resources Department, but here we developed that. We looked at wastewater treatment facilities in Maryland, looking at the amount of discharge, technology that they're being used, and the distance from the agricultural sector or farms that need water. We looked at land cover classification. In Maryland, there's a different regulation and guidelines, so we only divided the crops into two groups of food versus non-food crops. So in Maryland, for food crop irrigation, you are only allowed to irrigate food crops that are being processed or not eaten raw. So you're only allowed, for example, to irrigate like grains and those types of crops. You cannot irrigate vegetables with treated wastewater. And we looked at the climate impact and watershed prioritization based on the climate impact. Same process, we combined those, we classified spatially to identify the hotspots that are most suitable for agricultural water use. These are the wastewater treatment plants, the location of those. These are different types of crops, food crops versus non-food crops. Groundwater prioritization based on different number of wells. So as you can see, most of the eastern shore has the highest prioritization because most, as I mentioned, groundwater is the only source of fresh water in the eastern shore in the coastal plain. And this is the water stress map. And then once we combine those, we get a similar result to California, but obviously with different decision criteria. This is an example looking at 4 different locations in the state of Maryland. So these are the location of wastewater treatment plants and the type of crops that are suitable for irrigation. As I mentioned, we only are allowed to irrigate food crops if they are processed or if they are not eaten raw. But we also looked at other types of crops in order to see if there are some potentials. If you look at, for example, watermelon, or which is becoming a very common crop in Maryland, that's also another option that if the regulation changes in Maryland, we can irrigate that or look into irrigating those types of crops as well. Now, let's talk about the hydrologic model and then combining this multi-criteria decision analysis with the hydrologic models in order to develop decision support system for the watershed scale, water resources management, and water reuse implementation. So in order to do that, we use the ArcSWOT soil water assessment tool, and we faced with some challenges in terms of calibrating or the model. I'm going to talk about this for a couple of minutes, and then what we developed in order to overcome those challenges and then integrate that into our decision support system. We selected 2 study areas. One was in California, San Joaquin Watershed, which is in the Central Valley. It's a heavily agricultural watershed. This is the watershed. It's a huge watershed. It's very complex because it has many different land use. It's also in terms of the size, it's a huge watershed. And in terms of data, it doesn't have enough data in terms of the gauge stations or stream gauge stations data. This is the land use. If we wanted to just simplify the land use, these brownish areas are the agricultural land in the San Joaquin watershed. And this, as you see, most of the land use or the most dominant land use in this watershed is agriculture. So we faced a few challenges. The first thing that we, not just for this project, but anyone that is doing SWOT modeling will face is the uncertainty with these models. And there are some ways to overcome that uncertainty, to use optimization algorithms for calibration and uncertainty analysis, and also looking at different techniques, optimization techniques that are available, and selecting the best one for the purpose of that model. We examined different calibration procedures under different uncertainty to simulate the stream flow in our watershed, and evaluated 5 different objective functions. I'm going to just briefly provide some of the results from this project. So in this project, we found that among those 5 techniques, so the SUFI2 algorithm provided the best predicted stream flow with good R-square. And also, do you see that in the results? This is simulated, the blue line versus the observed, those dots, brownish orange dots. And then we use that, but still we wanted to improve our simulation. Also, we wanted to look at crop productivity, or the amount of crop that can be harvested in different areas. And we wanted to use the SWOT model, but we wanted to have a better simulation of the real world condition. So we decided to incorporate the leaf area index into our model. So leaf area index is something that you can get from the remotely sensed data. It's based on the quality of vegetation using the remote sensing technique. So we integrated that into our SWOT model in order to improve our hydrologic model. So this is where we integrated the direct insertion of remotely sensed daily leaf area index into our SWOT model in order to better calibrate our model for stream flow and crop yield simulation. And these are some of the results that I'm going to present. I'm not going to go into much details about this, but this is, so the red line is simulated an integration of SWOT and leaf area index. And the blue line is the observed data, and that the black line is the difference between the observed data and simulated SWOT LAI model. A comparison between just using SWOT and using SWOT plus LAI assimilation. The graphs on the left is just using SWOT. On the right are a combination of leaf area index and SWOT model. You see the improvement in the model. So for example, if the bottom pictures are showing the standard deviation from the MODIS, which is the remotely sensed evapotranspiration from the satellite data, you see the standard deviation is much smaller when we combine, so this picture, when we combine SWOT model with leaf area index. It's closer to the observed data. And for those 2 types of crops that we evaluated in our previous study, almond and grapes, this is what we get in terms of crop yield projection improvements. So let me go through these 2 figures. So the blue columns are the SWOT, only SWOT model. The orange columns are SWOT integrated with leaf area index. And this is, so the gray line or the gray area is from the agriculture survey. So these are observed data, basically. So you can see the SWOT combined with leaf area index provided closer to reality in terms of crop production projections for almond and grapes compared to only using SWOT model, both for almond and grapes. Then we looked at water reuse potentiality, or the potential for implementing water reuse in different watersheds. So these are the two watersheds that sub-basins that we included in the Sandwalking watershed. And these are the location of wastewater treatment plants in each of those sub-basins, major wastewater treatment plants. And we developed, so I'm just providing some of the results. We also looked into how much water we can save by implementing water use, but also combining that with different irrigation technologies, like regulated deficit irrigation, auto irrigation, regulated deficit irrigation coupled with auto irrigation. And these are the amount of groundwater that you can save under each of those scenarios if you implement water use combined with those different irrigation technologies. So these were some of the examples that we used in order to develop decision support systems, combining hydrologic models and spatial multi-criteria decision analysis. Now I'm going to talk about a different approach for water resources management, still used for implementing water use for irrigation, but a different approach. We're going to talk about the micro level dynamics of agricultural water reuse and how we can simulate that using agent-based modeling. So that's the work of my other PhD student that he finished a couple of months ago. I'm going to just provide some of the results from his work. So these are the locations of all the publicly owned or major treatment plants in the US. And different colors are showing different discharge types. The red one is reuse for irrigation. The green ones are spray irrigation, and then the rest are other reuse practices. In terms of numbers, though, spray irrigation only accounts for less than 2% of wastewater that is being discharged in the US. So only less than 2% of that is being used for spray irrigation. Less than 1%, this 0.8%, is being used for irrigation. So basically agricultural water reuse. Most of the treated wastewater in the US is outfall to a surface water source, 82%, and then direct discharge to the ocean, 10%. So there is a huge potential for agricultural water use in the US. But there are some challenges. So there are some challenges in terms of farmers' acceptability for implementing water use. So we wanted to incorporate that into our decision framework. We wanted to see how farmers are receptive of implementing water use in agriculture. We use agent-based modeling. It's a computational method for simulating complex systems. And let's talk about that in like one or two slides. What is agent-based modeling? For those of you who are not familiar with that, it's basically for simulating environment through simplifying it into a few different agents and an environment, and then assigning different characteristics to those agents in order to simulate a complex system. There are some benefits in using ABM, capturing it is able to capture emergent phenomena, including geographic, social, science network in the model. I emphasize on this aspect, social factors. This is an important benefit that you get from ABM, including different elements of randomness in the model, and we can create different types of agents, autonomous, heterogeneous, adaptive, and how those agents are reacting with each other. In our study, we looked at, it is based on a survey that was conducted as part of the Concept project. So they did a survey both in the Mid-Atlantic, in Maryland, Delaware, and also in California, collecting different demographic and socioeconomic factors from the farmers, like their attitudes toward using treated wastewater, and then some demographic factors like their race, gender, level of education, age, level of income, and then some other factors like financial factors. And then we use that to develop a model to see if there is any impact from those socioeconomic factors or characteristics on how farmers are implementing water reuse, both in Maryland and in Delaware, in California. I'm just going to talk about our study area for the sake of time that we did in California. We selected the Puerto Water District. It is in Central Valley. It's in San Joaquin Valley. The area of this water district is 45,000 acres, and it is between three counties of Stanislaus, San Joaquin, and Merced counties. And there are two major wastewater treatment plants, one in city of Modesto and one in Turlock, that they're thinking about providing treated wastewater from those treatment plants to this water district. They're able to provide, it's a significant amount, 140,000 acre-feet of treated wastewater to this water district. So there are some advantages if you compare ABM to traditional modeling. ABM can include heterogeneous agents, but traditional models can only include homogeneous agents. ABM can look for mechanisms behind a phenomenon. For example, in this case, how farmers adopt water reuse. Agents in ABM can be connected through a network. We can come up or develop a network that agents are connected with each other and impact each other's decision. And agents are adaptive in ABM. This is our study area. So we divided the study area into cells of 22 by 32. Farm sites were collected from the USDA database. There are, if we divide the water district into northern, central, and southern areas, there are 106 farmers in the north, 130 in the central portion of this water district, and 34 farmers in the south. So each of those farmers are representing, these agents are representative of each of those farmers in the model. And then they have different characteristics, obviously, in terms of the size of the farm, the crop type that they are producing, and then different socio-demographic characteristics that each of those farmers have. And then we developed 4 different scenarios: normal scenario, moderate drought, severe drought, wet condition. Then we simulated the area to see what would be the impact of those socioeconomic and climatic scenarios in terms of how many farmers will implement water reuse and what will be the impact on water resources in the area. I'm just going to provide two of the results. This one is showing the number of adopted farmers based on different scenarios. So how many farmers will adopt water reuse? So we assume that at the beginning of the simulation, none of the farmers are using water reuse. And we wanted to see what will be the impact on implementation of water reuse by those farmers. And this is what we get. Also, in terms of total recycled water consumption over the years, in the next 80 years, under different scenarios. That's what you can get from this ABM combined with hydrologic modeling framework that you are able to look into socio-demographic factors and their impact on water resources management. So these were some of the examples of the projects that we have done in our lab. What we are gonna do in next, so some of the future works that we are planning to do or we have already started. So one project that we just started a few months ago is we are trying to integrate socioeconomic factors with the geophysical factors in water resources management. So you want to see not just for water use, that example that I provided, but what are the socioeconomic factors and how they impact the water management in terms of implementing different irrigation technologies, for example, in a watershed, or developing different best management practices in a watershed for water conservation, for water reuse, for example. We are also looking at alternative water sources, a project that we started a few months ago. We're working with State Highway Administration, looking at use of alternative water sources for salt brine making. So brine is a practice. Instead of just spreading salt on the road during winter time, they're also using brine or liquid salt, but they're using a huge amount of fresh water, basically just tap water in many cases, to produce those salt brines. And they're interested in using alternative water sources like stormwater management or stormwater or reclaimed water for wastewater treatment plants in order to reduce their environmental footprint. So that's another project that we are helping State Highway Administration to explore different options. We also would like to use AI, artificial intelligence, machine learning, and implementing those new technologies in water resources management. That's another project that we are trying to develop. We submitted a proposal to NSF. So Adele is here, Paul is here, with a couple of other colleagues across the campus. We formed a team to look at this. Also under the grand challenges, we are trying to implement those new technologies in better optimization of water resources management. So these are some of the projects that we are planning or we have already started to work on. And with that, I'm going to end my presentation for today. If you guys have any question, I would welcome your questions. Yes.
You mentioned that in your recent research, you are integrating socioeconomic factors. At what area you are considering payment for ecosystem services or payment for watershed services among those your topics of your study?
Yeah, that's a very good question. And so we haven't done it in those projects that I presented, but we are looking into that, especially for urban areas, for example, where we have urban areas, that's a social benefit, the ecosystem services that we can get. But that's a great point. In those projects that I presented, we didn't look into that, but we are planning to. Yeah.
I guess just wondering with these like DSS, like these systems, have there been, or like how does that then become implemented, and like is that mainly getting into policy and whatnot? I guess like past the research.
Yeah, so it depends. So it could be, so decision support systems can be used by different stakeholders. Some can be used by farmers, for example, if they wanted to select between different irrigation technologies. Some can be used by policymakers, like people that are making decisions, for example, in the Maryland Department of Environment. Some can be used by extension agents, for example. They can recommend different best management practices to farmers. So depending on the stakeholders, we can implement those depending on the outcomes of the DSS and the stakeholders that those DSS are developed for. Yes.
You utilize the SWOT model.
Yes.
And a lot of people do. I've not used it before, but you hear about it all the time. Could you talk out loud briefly about what its perhaps unique virtues are relative to other hydrologic models? And it sounds like it does a lot more than hydrology, but getting it right from your talk. So maybe talk about what makes the SWOT model so great that it's used it seems. And will the SWOT model become more or less important as AI becomes more dominant?
So I was answering that the first question maybe requires like a specific lecture, maybe to just go over SWOT. But in general, So first of all, SWOT model, soil water assessment tool, is a model developed first by a couple of people at Texas A&M a couple of years ago, and it has become a very well-known model. And I would say, because the level of support that the model provides, and also in terms of the outcomes that you can get in order to, so not just the SWOT model, if we just go one step back, we use models to simulate something, right? Simulate a phenomenon. And when we wanted to simulate a real world condition, we have to first test and see if that model is able to simulate or be as close as possible to this, to the phenomena that is modeling. And SWOT model is able to, especially in agriculture and water resources management, looking at the results to simulate hydrological processes in different watersheds. So I think maybe its capability is one of the factors behind that it has become a popular model. So that's one thing, the level of support that you can get, and it's actually the community that is supporting and improving the SWOT model, maybe is another factor behind it. And therefore, for instance, they're actually developing since a couple of years ago a web-based open source SWOT model. So instead of just downloading SWOT on your computer and using it, there's a web-based version that you can just use that using their servers. There are those kinds of factors as well behind that, I would say. I don't consider myself an expert in SWOT. I use SWOT in my research. But for example, Adel is sitting here, he's a SWOT expert. He might be able to better answer this question. But
whatever expert means, right?
Yeah, but as a user, that's what I get. Yeah.
As you mentioned, and as Masoud pointed, it's a hydrological water quality model. It is based on a state curve number, so calculation curve number to the hydrology. There's option also to run on infiltration, greenhouse infiltration model, meaning to take small increments because the CS curve number is daily. But that's more of a hydrology to calculate surface runoff, subtracts from rainfall, implicate the rest, goes to the storage routing, to the source profile, replacement, and so on. Then there's lateral flow that goes to the rain. Along with that, then nitrogen, phosphorus, how much that grows the crop. You apply the input, how much you apply, in what form, organic, inorganic. It goes through the mineralization process and all of the above. All of uptake by crop grows. It is also taken off depending on how much you have in the soil, when the water is moving, when it is applied. So it's very complex. And then there's, phosphorus, the same thing. You can actually do subroutine for bacteria, environmental data. So it's there are many hydrologic, but one of the things that Masoud kept saying support, one of the things that the universities we lack, ARS, as in Temple, Texas, big group. Jeff Arnold, who was initial developer of SWOT model from his PhD work in Illinois, SWOT model that extended into SWOT model. He's there in Temple, Texas for many years. He has probably 6, 7 people there that, you call, they can answer your questions. My point is, when we get grants, in 3 years, we develop models and then we move into another grant. We don't have any support to move that model into the stage where you can use, we can answer your questions. If you call, maybe I'll help you half an hour, but that's about it. All I'm saying is there are lots of, that's why Masoud is saying there's support behind it. So that really is the key to consider in use of these models. And there are AgNeps, there's, Greens original dividing in Georgia. So there are lots of these hydrological. Sorry, I hope
That's great. It's great for everybody to be aware of this, what's behind it, why it's so good.
Yeah.
So I'm wondering, Masoud, in this scope, the big scope of sort of water reuse, obviously places like California, Maryland are very different, but let's say locally here in Maryland, what do you consider to be sort of the primary limitation for people embracing and adopting, implementing water reuse strategies? I mean, do you have sort of a general sense from the work that you did, sort of what's, is it infrastructure, is it sort of policy, is it people's reluctance to kind of do new things or to put wastewater on? I mean, do you have a sense of sort of what's the major block?
Yeah, so
Impediment?
yeah, excellent question. If you want to answer this question, it depends on how you look at it. If you look at the water reuse very generally, I would say both the people's attitude to water reuse, it's very different in Maryland versus in California, Arizona. That's one factor affecting this. The other is policy, which could be actually an outcome of people's attitude, because policymakers are from the people. So when they're setting those policies, that's the mentality behind it. So policy is also an important factor, is that, and because in California or other Western states, they have been facing drought, so that's a big driver behind it. But then if we break it down into different sectors like agriculture, urban sectors, different sectors, that could be a little bit different. For example, the project State Highway Administration, the project that we just started. So they're using just tap water to make brine. So they can easily you can capture stormwater and use it for irrigation or reclaim water or other types of water. So like they can build a pond, for example, next to the brine making facilities. We have 15 of them throughout the state of Maryland. They are becoming more aware of that. And so and they are more receptive compared to, for example, farmers. Farmers, once they realize that after those like seasonal droughts, for example, in Eastern Shore, when they see that by irrigating, they can significantly increase their crop productivity, and they can make much more money compared to not irrigating. So economical incentives or the benefits they can get, that could be a driver behind it for farmers in this Eastern Shore. That's why actually they have started irrigating many farmers to make more money. So many different factors behind it, but I would say policy and attitude is very different here versus Western states. Sure. Yeah.
I'm assuming that when you use wastewater, you're putting a lot of things into the inputs of the system, and then people monitoring the water to ensure that the water stays and that it doesn't have contaminants in it, such as like forever chemicals. What I guess with your research looking at maybe like the risks of this having factored in, looking at if the contamination risk that people assume when they accept wastewater, and then also like if this is like an enduring concern.
Yeah, it is a legitimate concern. It was so it is out of the scope of the work that we are doing. They're not doing any like environmental or human health risk assessment, but it's a legitimate question. And as a matter of fact, the Conceptual project that I just mentioned briefly, there was a huge project. One of the components of that project was to look into the microbial quality of the reclaimed water and what are the potential risks behind using reclaimed water for different purposes. So that's an excellent question. So, and adding to that, actually, not just for wastewater, even for drinking water, the water that you're drinking from the tap water, the standards that we have in US or not in any parts of the world, they are not comprehensive. The newer contaminants, the emerging contaminants that we are able to detect the recent improvement in the technology, they are not part of the regulations. And as a result, not the drinking water treatment plants or the wastewater treatment plants, they are not monitoring those pollutants. And you can see them even in the drinking water that you get from the tap water. That's a huge challenge.